Okay, now we're going to keep going. My camera died. So, we have the I total, and what we wanted to know is the voltage drop of resistor 3. So, in other case, we just are going to math out the voltage for resistor 3. And to figure out that, we're going to use, just to kind of understand what's going on, how we're going to figure out the voltage of resistor 3 is we're going to use the changing thing in the resistor, which is the resistance is changing, of course, against the thing that's not changing, which is the current. And doing that with the information we have now, we're going to be able to figure out that changing voltage with the changing number of the changing resistances. Okay, so we want to know E, and we have I, and we have R. So in that case, like I was saying, we have E, I, and R. So we do I times R. Good way is you just put your finger on. So we want E, we're looking at I next to R. I times R. So I would be I total times R3. And it is a good idea to label what you're doing. E3 is I total times R3. So if you get confused or stressed, you can actually look at it and really clarify, okay, yes, that I'm going to be doing 1.8 times 15, and I know that. Okay, so let's again, always on the calculator. Even if you think you can do something in your head, the only time you should ever do something in your head is when you can glance at the paper and tell the answer, and that's normally something like 5 times 10. So 5 times 10, that might take more time to take out your calculator than not. But other than that, you should do it on a calculator so you can see what you're doing. 1.8 times 15, 27. Double check. 1.8 times 15, yes. 27. That is the answer of the total resistance, or the, not total, but the resistance of the, let me mumble jumble, sorry. That is the voltage of resistor 3. Sorry. Okay, voltage of resistor 3. That's why before I jump to anything, also double check what you're doing and rethink. I've spent a lot of studying, so. And it's a little different, you take a video as well. So now, the question above, we did that, so now we're doing number 3. What is the total voltage described in the circuit? Okay, so now remember the voltages add together, and we could figure that out by figuring out each separate voltage and then adding them together. We already have this one, we already have that one, so we just have to do one more, but then we'd have to add them. That would take 2 steps. 2 different things we'd have to solve for. So what's maybe a shorter way, which is always a good way to think, or maybe even a simpler way because of that, is if there's something that could take 1 step, for example. So if we want to do 1 step, we could just take the total resistance of the entire thing, added together. We already did that for the first answer to the first question. And then the total current. In that case, we'll find out the total voltage, because now we don't have the changing number in each resistor. We have all of them added together. So now we can also get the total voltage. Okay, so let's do that. So let's also write down what we're doing. So number 3, that was also number 2 right there. Number 3 is the E total. And to get that, I have I and I have R. I'm going to pull out the paper, whatever you have. I have the flashcard. Actually, I have this one. This one's neater. So I have I and R. So I'm going to do I times R again. You can double check right there. It's always actually good to double check. So you write, I like to write it down. E is I times R. I'm solving for E. I have I and R. You double check here real quick. Okay, I want E. I have I times R. Nothing can go wrong if you do that. And then I have 1.8 times, in this case 50, because that's my total. So my R total, I total. 1.8 times 50. Calculator. I'm going to go a little faster as I go. There's a lot to explain here. A good amount at least. 90. however way you want to look at it. I think it's quite a lot. 90, and 90 is what? That is the E total, because that's what we're solving for. So that's our E total. Now we have the total voltage. Okay? And again, this is because this is a series circuit, and so in this case we added all the resistances together. All three of these are for series. Okay, so now let's do for parallel circuit. Actually get a new paper out in case I run out of room. So same questions, but now instead of the series circuit, we're going to be working with parallel. Starting with the first question, which is now actually completely different. We have the 3 resistors. Again, it's good always just to write things down. 3 resistors, we want the resistor total. Okay, so we want the R total, and then we have 3 resistors after that. It's a good way to kind of do it. R total, then you have 3, or you can just write down 4, but to not complicate, you do R total, then 3. So I do 1, 2, 3. I just like to do things quickest. It's quickest for me. 25, 10, 15. We already wrote this down, but now it's going to be a completely different answer. We're going to want this for the other stuff too. Good to write stuff down. Separate the total from everything else. 25, 10, 15. And now what we're doing is solving for the total. So to find out the total of the resistances, I'm going to write down what we're going to be doing. So our total is equal to, you're probably not going to want to write this down every time you're doing this, but I got to show you. So you do 1 over R1, RT, R over R1 plus 1 over R2 plus 1 over R3, and of course, as you can imagine, if there were more, it'd be 1 over R4, and so on. So here we have 3, so we're doing that. That's our equation. Our total is that, but it's more than that. Our total is equal to that. How do you write this down? I would say then that equals, what this equals, let's say that is blank, or I'll call it n, 1 over that number, okay, is going to be your R total. Okay, so let me explain that one more time. If we want R total, we're going to have to do all this stuff, and that's going to equal a number. Then we're going to get that number, 1 over that number is going to be the R total. So let's do that. Okay? So your calculator recognizes PEMDAS, okay? As you may remember from algebra, I think it is. Parentheses, exponents, multiply, division, add, subtract. So that's the order of any mathematical formula. And, of course, calculators will know that. So you can simply do 1 over 25 plus 1, I'm trying to get an actual shot here, 1 over 10 plus 1 over 15. Okay, here you go. And now we're going to equal that. We're going to get let me get a little better, 0.206. Okay, so it's good to remember one thing. It's kind of funny, but you got to remember this. Go to the thousandth. So that'd be 3. You have your tenth, hundredth, and thousandth of a decimal. And always, when you're doing these for the electrical questions, figure out your thousandth, and then keep in mind that the answer might be based off doing math off your hundredth, maybe, and there's a good chance it's going to probably be off your thousandth number. But if it's slightly different, you're like, what's going on? Do the same thing with the hundredth of the decimal that you have instead of the thousandth number, and you'll probably get the exact answer. Okay, so it's just a little weird. We'll see what happens. I'm giving you the answer here, but you'll see that's what happens. Okay, so we have that total, and just to double check, it's good to double check everything. I had 1 over 25 plus 1 over 10 plus 1 over 15. Everything's looking good. Okay, and also the answer's looking good. Now I need to remember that's 1 over that equals my R total. So what's 1 over that? And normally, as you'll see later, instead of writing all this, I'm just going to do all this in my calculator, and then I'll write this 1 over that. So at least that's written down. Now I'm going to keep this on my calculator without clearing everything. I'm just going to start a new thing. 1, so now I can still see what I'm doing. 1 over 0.206. In this case, if I wrote something down and I was thinking too quickly, now I can see it's on my calculator right in front of me. 206. 1 divided by 0.206 equals 4.854. Okay? So 4.854, whether they want to add that 4 in there, doesn't matter because it's still going to be 85 no matter what with the 4 there. Okay, so 4.854 is our R total for the resistances. And I said this is what I do, and I normally do this and I forgot to do it, it's a parallel circuit. So write P above it, and I make sure there's enough room for that. So I leave a few spaces. And now I know everything in this is a parallel circuit. Okay? And as you can see, our total is 4.85. It's almost 5. That's smaller than all these. So in a parallel circuit, your total resistance is less than all of your actual resistances on your resistors. Okay? Also, really good to know. That might be a question. Okay, so then we need same thing in the question above. If a voltage drop of 45 volts is measured across R1, what is the voltage drop of R3? Okay, so now same thing. We have a voltage drop, 45 volts of R1. So in this case, I'm writing 45 E. I'll do a quick little line to separate that. 45 E, double check. R1 is what they wanted, 45 R1. Then they want the voltage drop of R3 is the question. So now, what is the voltage drop of R3? So now we need to remember we're working with a parallel circuit. So what happens in a parallel circuit is the current adds together. It is not the same on each resistor, but it can be added together to get your total. Okay, so it changes. Your voltage stays the same though. So if the voltage stays the same, then we know that actually resistor 3, but also resistor 2 is 45 volts. And furthermore, the next question asks, what is the total voltage described in this circuit? Okay, so we also know, well, if the voltage stays the same in a parallel circuit, well then the E total is 45. Okay? So now we know resistor 1 was the question, but we also figured out resistor 3, and we didn't even need to know, but we know resistor 2 and the total resistance. It all stays the same. So as you can see, when you're working with a parallel circuit, all of a sudden adding your resistances together becomes a lot more difficult. It's like, whoa. But then you have a question about your voltages, and you see how simple that was. Okay? So it's kind of interesting how they change so much. Okay, so I have some more questions here. These ones are more specific to where we actually have, this one's actually asking for a parallel circuit. So we have 3 resistors in parallel here. Okay, and as you saw, the first one, that's how it asked the question. I'm going to change the question a little bit each time. And you see here we actually have a schematic. Okay, so there's going to be something else after that too. This is going to be just 3 resistors in parallel. And you see we have R1, R2, R3. I kind of labeled it how I label it. 10 ohms, 14 ohms, 30 ohms. And we have 0.3 amps on resistor 2. How much current flows through resistor 3? Okay, so that's the question 4. I should probably separate that to make that a little more clear. Okay, so we have question 4 there, and we have those 3 resistors in parallel, and now we need to remember that the current does change, so we don't have the current just staying the same. So how are we going to figure out the current with all this? Okay, so a good way to figure out, we have 2 changing numbers. Let's think of that. The resistances are always going to be changing, and also the current in a parallel circuit is now changing. So because of that, we have these two numbers that are changing. So how are we going to figure out these two changing numbers? We need a number that doesn't change as a constant, so we can base basically the entirety of what's going on. Get a non-changing number is a good way to just simply explain. We need a non-changing number to be able to compare with one of our changing numbers to figure out our answer. Is just the simplest way to explain that. So what's a number that's not going to be changing? Okay, so let's think. We have a parallel circuit. Our currents add, our voltages stay the same. Okay, so since our voltages stay the same, because the voltages stay the same. I have to think about this stuff right now. When I'm taking a video, it's so much differently than when I'm just thinking about it. We have that number. I just want to make sure that I don't also teach something that's incorrect. Okay, so we have number 4. We have those the voltages staying the same. I can't even talk. Okay, so we want our E total, or not even that. We just want E. Stays the same, so we don't need to label it. How are we going to figure that out? We have R, and we have, I should label this I actually here. It's a good thing to do, just so you can glance at it. See, we have R, and we have I. Okay, so again, handy dandy flashcard in my case. I'm going to make this a little better as I go. So I want E and I times R. I times R. So it's good to remember, write it down. I times R. This one doesn't matter that much. It's a good habit. And then we have 0.3 times 10. Okay, so that's our I times R. Oh, wait. I hope you caught that. Sorry, it's a little weird when I'm filming, because I'm not looking at what I'm doing half the time, I'm looking at the screen. It's just a weird disattachment. But here we go. We're solving for resistor 2. And that's the information that we have. So because of that, we have our two changing numbers, and we want to get our, basically, I2 and R2. Okay, so that's what we have. I2 and R2, as you can see, we're going to multiply those together. So 0.3 times 14 equals 4.2. 0.3 times 14, 0.3 times 14, double check. 4.2 is my not final answer, so I like to circle it. Or actually, that is my, let's see, how much current flows through. Oh no, that's not my final answer. So that's what I thought. This stuff's kind of funny. It makes you really have to think a lot. So how much current flows through R3 now? Okay, so now we want R3, so I'm going to kind of underline, identify. Okay, R3 question mark, okay? So now we want R3. We have, of course, our E total that doesn't change, so that's everything. So now I'm going to call that the E total. We can use it for everything. We need to understand that. Working with a parallel circuit, so we should label it parallel circuit. Okay. Now, R3 is going to be working with E and, how do I say this? Yeah, my E and my E and my R. Okay? So I have my E and my R. E over R. Oh wait, I'm working with E total and I want R. So yes, I'm working with R3 4.2. Oh, I'm so sorry. It's not the first time I've done that. So it's maybe not bad seeing my mistakes, because I was thinking, oh, I'm doing the current of resistor 3, and I wrote down R3. So no, we're doing the current of resistor 3. So okay, that's why I should have labeled it I3. So you saw me mess up and confuse myself. Okay, so now we want that. We have the constant number 4.2. So we have the E and the R like I thought. E over R equals I. Okay, so E over R, but hold up, it's not just E over R. E stays the same. It's E total, but it is R3. So now that we identified that, we can obviously look and we can get E total, which is 4.2. And we can divide that by our R3, which we can look is 30. 4.2 divided by 30. Double check. 4.2 divided by 30. Yes, that is 0.14. Maybe not the best square. Okay, see, 0.14, and now I have my I3, which is the answer to the question. So the current flow through R3, we have I3, we have 14 amps is I3. Okay? Now number 5 is saying, what is the I total? What's the current total of all this? Okay, so remember, we could figure this out a few different ways. Let's try to think of the simplest way. If we want the current adds together in a parallel circuit, of course, but we'd have to solve for each of the individual ones. We could write this down. We already have 0.14 amps on this one. Okay, now we need this one. So if we just solve one more and add them together, we could get that. There could be another way if we had the I total, and if we had a different number that works, we could figure that out, but we don't. I mean just another number that was totaled, but we don't. So I think the simplest way here is to actually just figure out the next one. So how are we going to figure out the next one? Do the same thing. So now we want our one's current. So we do I1. Okay. And we have R and we have E. Okay. So E over R, I should show you. E over R. Double check. I is E over R. Okay, good. It's not just E over R though. It's E total over R1. And that's I1. Okay, so it all makes sense. It's good to just look while you're going along. Then because of that, now I have E total 4.2. I'm going to divide it by R1 divided by 10. Okay. Calculator. 4.2 divided by 10. 0.42. Okay, and that is my current of that one. And now I'm going to have to add them together. Oops. 0.42 plus 0.3 plus 0.14. Okay, so 0.86 is my answer. Double check. 42, 3, 14, 86, 0.86 is my current total, otherwise known as my I total. Okay. Now my next question. Okay, so we just did some ones that were more descriptive. They told us what we were working with. The first one was more like a question, like a, I forget what you call those, a word question or something. This one was more of just a question of giving you information that you're just kind of looking at, plain and simple. This one is more of a visual, what they would call a schematic. So here you actually have an electrical schematic. Let me reposition this a little bit. And so how are you going to work with this electrical schematic? And how are you going to see what's going on? Okay, so I did show you in the beginning, but as we can see here, this is a series circuit. Why is this a series circuit? You see, it won't explain that. It's just showing you. Okay? So we can see that the resistors run in series. This one goes to this one, which is in a series, to this one, which is in a series to this one. So if something happens to this one, you can see where it's going to affect this one and the ones downstream from it. Okay, so it's also good understanding, but we can visually see the actual series circuit here. We can also see we're given some information. It's good just to identify before you do anything. Okay, so what we have is we have all of the resistors they show us. So it's also in series, so we are also able to add these together to figure out our answer. The total resistances, okay? And then the resistance total, however you want to call it. And then we are given the volts of this circuit. So this could also be known as the E total, right here, the 60. So how much power is dissipated by the 120 ohm resistor? Okay, so we need to think about something here now. Is that the voltage is going to be changing. So let's just think about a series circuit. A series circuit, the current stays the same, and the voltages don't. They change with each resistor, and because of that, they can add together to get your total, and so can your resistors. So basically, whatever these numbers are added together are going to create this. So these are pieces of the total voltage. That's one way to think about it. And these are also pieces of the total resistance. Okay? Remember, it's completely different in parallel, but this is series. Okay, so we're looking at a series circuit. I probably wouldn't do that in a real life situation because you can see it. But in this case, I'll do an S above it. We're going with the series circuit, and we want power dissipated by the 120 ohm resistor. Okay? So we're thinking about power. This is an interesting question because because what we're given right now is the total voltage. So you might just think, well, obviously, we're just going to figure out power. We're going to use P, we're going to use E, we're going to use R. We're going to figure out a formula for that. So if you had P, E, and R, well, in that case, you could just do P equals E squared over R. Okay, that would be your formula if you wanted P. But there's a problem with that, is that these volts are going to be changing. So you can't use a total voltage to get any of these numbers. You can't use a changing number that's going to change on each one of these to find out this answer. Because this answer is going to be dependent on the voltage of this resistor. So all the other ones. This will have its own voltage. This will have its own voltage. They change and they add. So because of that, you want to find out the answer using voltage for this resistor. Well, you're going to need to figure out the individual voltage. So if we call this resistor 1, 2, and 3, well, then in that case, I don't know how I'd label that, but you can see 1, 2, and 3. Then in that case, we need to find out the E2 if we want to find out the P2. It's kind of funny saying that, but that's what we're going to have to be doing. So, again, we have two changing numbers. We have the voltages change. We also have the resistances change. So we're not going to be able to have these two changing numbers in this scenario with what's going on and figure out the answer to this. Because like I was saying, we need to figure out this voltage to even figure that out. So what's going on here? What are we going to do? Well, remember, we could figure out the total current, and we could figure out that current is also going to be, the current stays the same in a series, so if we figure out the current, then we will figure out all of the current. Okay, so then in that case, how are we going to do that? We're going to need to add we're going to need to figure out the total resistance, okay, because we can't just figure out this off that and also find out the current. Remember, these are two changing numbers. We need that one number that stays the same to figure out what's going on, to figure out our different changing number is a simple way to explain it. Okay, so in this case, we're going to add all these together, series circuit, very simple. So we're going to do 60 plus 120 plus 40. Doing my calculator. Okay, double check always. 60, 120, 40, 220 is the answer. So I have 220 is my R total. Okay, so I have E total, I have R total. So how do I figure out what I'm trying to figure out is my, I'll call I total in this case. Okay, kind of running out a little bit of room here, so I'll put this up here. Okay, so I want to figure out my I total. And remember, I have my E and my R. So I'm looking at the handy dandy flashcard. I want I have E and R, so it looks like that's E over R. Okay, so E over R, double check, I is E over R, yes it is, okay, and that's all totals, so now I have 60 over 220. 60 divided by 220, and I'm looking at 0.272727 repeating. Okay, is another way to say that. So my answer is 0.27 repeating, and yes, I did 60 divided by 220. Okay, so I have my 27 repeating. Whenever a number's repeating in a decimal, you can put a line over whatever section's repeating. That means it keeps repeating. We have two numbers repeating. Put a line over it, means 272727. Helps you remember if you can't find the right answer, you can start adding a bunch of 27s, see if it gets closer to your answer. Sometimes it works. Okay, so now we have the I total. I should actually wrote down what I was doing. So 60. Sorry if it's messy. You get the point. 60 over 220. Okay, and it's 0.27 repeating. Okay, and I actually erased that, so now I need to redo that. 60 divided by 220. Yes, 0.27 repeating. Okay, never get cocky when you're doing any of this, because you'll most likely make a mistake when you do that. Somewhere at some point. Okay, so now we have the I total. We don't need to know the I total, though. The question's asking, well, the first question is asking what's the current through our... Oh, wait. My bad. The question's asking how much power is dissipated by the 120 ohm resistor. So we haven't worked with watts yet, but now we're starting to work with watts. Okay, so we want the 120 ohm resistor, remember, is what we want the P of, and now we have our constant number. We have the 0.27 repeating. Okay, so remember, always stick with the thousandth. I said that, and I didn't do it. So your 27's repeating, but then you have the 2 after that. That's probably going to give you the answer, or that one. Either one is basically most 100% probably going to be the answer. Okay, so I want P. Not only P, I want P2. Okay, and I have the constant of, always label it, my I total. Okay, so now my current of the whole thing, whatever resistor, it's the same. The total is the same. It's the same through the whole thing. Okay, and handy dandy flashcard time. I want P, I'm looking for P. I have I, and I also have R, because I'm looking for this resistor. Okay? So I, R, and P. Okay? I have this one. So looking at P, it looks like that's I squared times R. Okay? Always write it down. Always also really pay attention to the square. If you forget that, your whole answer is wrong. So P 2, big 2, is I squared times R2. Okay, and in other words, that's the same, that's saying that I squared is 0.272 squared, and then I'm doing times 120, R2, okay? Take out the calculator. We could do two things. We could do point to figure out our square. 0.272. A square is multiplying it by itself. So we could either just do 0.272 times 2, or you could do it simply and use the square root button of your calculator. Whatever you want to do. you'll get an answer. Same thing, 0.073. Okay, so now we have 0.073, and should I write that? Yeah, I like to write everything down. So now we have that new 0.073, and then you can just from there, instead of pressing any number, directly press the next thing, was multiply. It says answer multiplied. So now we're going to multiply that answer times 120. Double check everything. 272 squared. Good. Times 120. You really mess up if you don't double check things. 8.87. Okay, and right to the thousandth decimal always. 8.878 in this case. Okay. Now that I have the actual number, I have my power of that resistor, or in other words, what they're calling the power dissipated by this resistor. 8.878 watts is power. Okay? And the next question, what is the current? Okay, so we already solved for current, and we know that's 0.272. All right. Now, the last one of our worded ones before we get on to some fill-in-the-blank questions, which are really good. We have this question. We have only two resistors. And actually, this one's a ABC. We have two resistors. We're working in parallel. What formula can you use? Okay, so in that case, it's asking you that, or you have a visual actual representation of that. Won't be the prettiest. You see, those are in parallel. They're not in series. Okay, so we have two resistors in parallel. What formula can we use to figure out the answer? Okay, and it only works for two. Remember that. That's the question, but it's also the fact that you can't do this for three, or you can only do it for two in parallel. Is it R1 plus R2 divided by R1 plus R2? Is it R1 times R2 divided by R1 plus R2? Or is it R1 divided by R2 times R1 divided by R2? I tried to trick you a little bit with how I said it. It was B is actually R1 times R2 divided by R1 plus R2. May seem a little weird, but if you say it enough times, it just sticks in my head personally. So, R1 times R2 divided by R1 plus R2. It was so weird, I just remembered it the first time. I was like, what the heck? How does that work? Oh yeah, and then I made sense of it. When you also, if you make sense of things, it really helps. Which you might have to sit there and hurt your head a little bit. When the end of it, you'll actually understand what's going on. Okay, so I need to take a break. I'll be back in a minute. Okay, I am back. And we have two different questions. And we can do them whichever way we want. But how I'm going to do it is I'm going to double check one thing and then I'm going to show you. Let's see. Yes. Okay. So I'm going to do this as a series circuit. And I'll do the other one as a parallel, which you'll see when I get to it. You don't see that right now. Okay. So I have series circuit, and it's basically just fill in the blank. So what's going on? That's good enough. Okay. So we have a series circuit. We're given minimal information. With this information, it is enough information to find out the rest of the answers, though. So we're going to have to figure out the rest of the answers. So let's get to it. So first, we can see we already have our R total, and we have these resistances given to us. We also know that in a series circuit, we can add these to get this. So if these are all, so if this is the only thing that's missing, then there's a few things we can do, but the easiest way is to add these together and then subtract our total by that to figure out what's missing from the total. Okay, so let's do that. So we'll do 35 plus 10 plus, oh my gosh, what did I just press? Okay, delete, woo, plus 15, 35 plus 10 plus 15, so I have 60. I'm going to do 75 minus, I guess I'll just write it right there, 75, actually I should just get my new paper. Okay, so working there for now. 75 minus 60. Why am I writing down so much stuff if you didn't already hear me say this a million times? I'm sorry. But it's because if at any point I get confused and I think, what the heck, what's going on? And if I did write down something wrong, I can see where I went wrong. And I can think, oh, I did 70 minus 60 on accident instead of whatever. So here's 75 minus 60. Okay. And that equals, obviously, 15. But I'm going to do it on my calculator so I can look at it if I'm stressed, especially, and look at it. So, okay, 15, yes, that's 75 minus 60. Okay, I can double check everything. The computer can do it for me. Now I have that answer. 15, and you can obviously add those together, which is basically what we just did, but you can double check everything that way. If you have some spare time, if you want to add things together. To double check things, it's a good idea. We also know that if we're in a series circuit, then our current is actually staying the same. Okay? It's our voltages that are going to be changing. So in that case, we already know all of the currents. So in that case, that makes us very helpful for what else we're going to be doing. I like to just go down one line at a time, because in this case, we already have the constant number. So now we have our other numbers that are going to change based off whatever changing number we use with our non-changing number. Okay, whatever we do, that's how we figure it out. We don't do two different changing numbers. And our power is always going to be staying the same. And if you want to do two different changing numbers, well, I mean, I guess you can, but you can't do the same number across everything. So you'd have to do the individual resistor that you're working with, which is, this will all click the more you do this. Okay, so we want E total, or I1, I2, I3, I4. Okay, so what's kind of the easiest way that we could be doing this? Well, probably just solve E1, E2, probably just have to do each one of them individually, honestly. Okay, so let's just start with the total. So how do we figure out, let's just figure out one formula when we're working with E, okay, and we want I and R. You probably already know this by now, but E is I times R. Okay, E, I times R, in other words, your ear, okay? So I times R, now we're just going to be doing that for every single one. So in another case, I times R. When you're multiplying, of course, you can do it either way. So in my case, I'll still do I times R because that keeps the same constant number from the base. So I can just 8 times blank, 8 times blank. So 8 times 75. 8 times 75 is 600. So you can see now I have 600. And before I delete that, 8 times 75, yes, 600. Okay. And then I'm going to do 8 times 15, and I'm going to get 120. Okay? And I'm going a little slower than I would in real life because I have to kind of double check it off the camera, and it's what it is. 8 times 35. Okay, so 8 times 35, we have 280. Okay, and then now we want, now I need to double check actually. Okay, and now we want 8 times 10. In this case, I was saying if you have anything times 10, my opinion for me, that is so simple that if I want to double check what I'm doing at the end, anything else might take me a second. If it's 5 times 3 or something, that's pretty simple. That might take me a split second, and I probably would still do that on my calculator because of that. But the simple things like 10 times 8, you can glance at that and without even thinking about anything, no thinking at all, just 80. You can literally, without thinking, at least for me. So because of that, I won't do that on my calculator, but I will do the next one, which is 8 times 15. 120. If you can already think of it in your head, then do it on your calculator. It's good. Well, there's no problem with that. You can actually get really fast at using your calculator. A lot of people use their text super fast. You can kind of be like that on your calculator. 8 times 15, 120. We're looking pretty good. And let's say you had extra time on your test. So now I'm going to, just off screen, I'm just going to add these all together. So 120 plus 280 plus 80 plus 120. Okay, and that's going to equal, as you can see, 600. Okay, so everything's good. Each individual one also equals that. So it looks like everything is darn dilly, is what I'll say. Okay, so now we want P, and we have, I'm running out of kind of writing room of what I'm going to explain this with, so let me erase kind of right here, and I'll write the rest right down here. Okay, so what do I want? I want my P, and I do want my P total, but I want all the P, so I'm kind of going to have to do the same thing. So what's the easiest formula? Because we have already multiple things filled in here. We can work with the E and I, we can work with the R and I, and we want the P. Okay, so what would be the simplest thing? I think if I won P and I did E squared, oh wait, no, I wouldn't do that. Or, I mean, I could actually do that. So let's think. Since I do have each individual resistor, I could get each individual math and figure out each formula for each one. I mean, I could actually do also my E to my R, thinking about it, because I have each individual resistor already here. I have all the information I need. So kind of let's look at the simplest numbers. So I have some big numbers here in the E, and I have some smaller numbers here, especially in the I, it's all the same, but smaller than the E is the R. So that looks like simpler to me. So I'm looking for a formula that has I and R and P. Okay, so I squared times R. Remember, small 2 square, big 2, the resistor. That's how I do it at least. Okay? So P, that's what I wanted. I times R, I squared times R. Okay? And that's all of them. So it doesn't matter which one I'm doing. I need to do it to the individual one, though, of course. Okay, so now let's figure out what I squared is. So we can use that as a base number. So first, I squared, 8 times 8. We should we may know that, is, I'm going to show you the other way. You just do 8 times 8. 64, one of my favorite numbers. Maybe my favorite number of all time. So if 64, I'll write that down. 64 times blank. Okay? That's going to be what we're working with. Okay? So 64 times each of the different R's. So 64 times 75. You can see 4,800. Okay? And we do 64 times 15. Get 960. Okay? And then 64 times 35. 2,240. Okay, and then 64 times 10. Oh, I maybe didn't have to do that one because that was times the 10. As you can see, 640. And then 64 times 15, and that's again 960, which we already did, and we got the same answer, so we can see nothing seems to be going wrong whatsoever. And we can also, we'd probably be doing this quicker in real life, so let's say we add them all together now, if we had extra time to be able to do so. 960 plus 2240 plus 640 plus 960. So you saw how quick that was, about a minute to make sure I had the right answer, so it's probably worthwhile no matter what. 4,800, that's all looking good, so we can see everything's working out. Since I already added everything together, you probably wouldn't need to do any further steps, but if you wanted to, you could take further steps to compare everything together and try to figure out that you have the correct answer. Like if I had my I total, and did I already have that from the... Yeah, I guess I just added everything. I just kept it the same. So let's say I wanted to kind of do some double check here, just to show you. Just maybe to prove to you. And I wanted... Where's a blank piece of paper? Now let's say I'm just looking actually for I total. And I have E and R is what I'm working with to get that. And maybe after that I could do something with P. So I total, okay, and where's my flashcard? Here we go. E and R, E over R. They're all total. Okay, so in that case, I would get 600 over 75 equals, it's going to be my I total. So I get 8, which is the same thing for everything. Okay? So we just kind of proved to ourselves that everything's looking good, and we do the same thing with P if we want. So we figure out, okay, so what formula could we use to get I with P and something else? So say I, oh, this is a good one. So just to show you, say we do have I squared is P over R. Okay? So in that case, what we do? Well, I total, but I total is equal to, the formula is I squared is P over R. Okay, so that's kind of weird because we're starting squared. And you may not want to pick, if you have the option to not pick a formula like that, you may not want to, but it's actually pretty simple when you wrap your head around it. You can also pick a formula that's already square rooted in another situation, but I'm not going to get into that. Okay, so just to double check, P and R, so what I was using, P over R is I. Okay, and how do I explain this? Since I squared, our answer squared is the total, or yeah, I squared is the answer. So whatever this number is, our answer squared is the actual total. Okay, so we need to think kind of in terms that this is separated from that. So what we need to do first is P over R. So do 4,800 over 75. So 4,800 over 75. That equals I squared. Okay? That is already squared. So now if we want to figure out what basically that is, we need to get the square root of that. Okay? I don't know if that's making sense, but we need this squared. How do I explain this? I guess that's, you kind of just have to know it like that. I squared, this doubled, equals that. So whatever this is doubled equals that. So if we get this, then we need to undouble it. I guess is a good way to think about it. Okay, so let's undouble it. We need to square root it. I mean not double it, but undivide it from itself. This is what square rooting is. So you could do, the how I do on my calculator is I do second, and there's a blue. The blue are the seconds, square root button, right there. And then I just type my number. Okay? And if it's not a squareable number, I'm going to show you what to do next. And then I'm going to get into the next fill in the blank one. Okay, so 64, we have 8. So that is a squareable number, as we probably know. We already did that somewhere. I don't remember where. But we're kind of... Okay, so we have 8. 64 square root of 64 equals 8. Okay, so now we can also think 8 squared equals this. That divided by that, which is true. 8 squared equals 64. This equals 64. And 8 squared equals 64. So okay, so you see where it's making sense now if you're starting with squared. I kind of wanted to show you that because it's kind of a weird one. You kind of got to think about it. But you just kind of got to realize if it's already squared, the best way to say it is you got to unsquare. If it's square rooted, you got to unsquare root it. Okay, so if you're working with I square root equals P over R, then in that case your answer, I'm going to change it back, but if it was square root, for example, then you'd have to get your answer and square it to unsquare root what the answer is that you got from this. So I'm going to move on, but just one more time. This divided by that equals a number times 2. So whatever this number times 2 is equals that, and that is 64. I mean, not times 2, but times itself. Square rooted. You know what I mean. Okay, so squared. Now what happens if you have a number that's not square rootable? We'll do simply 65. So on a calculator, and it'd be similar to in real life, but it's kind of complicated. It's easier on a calculator. 65. You press enter. Well, that doesn't give me anything. I got the same thing. So I got 65. So what do? In my case, I press this button that has these 2 arrows side by side. It took me a while to figure this out. These 2 arrows side by side. Okay? Click those. Or it may be the fact that it's the equal sign that's squiggly. The rate, I forget what that means exactly. No, it is the 2 arrows. Okay, that's what I thought. And then you get 8.062. Okay, so you get all that. So it tells you the answer. And let's say we had... Yeah, sometimes it'll actually show you how it breaks it down into a squareable number and a non-squareable number, and it figures it out that way. It does like something to the degree of something, but in this case, I guess it's just showing you the plain decimal. Okay. So Don't really need to get into decimals too much. There's a lot can do about decimals, but we have all of our answers. We solved for everything. We also figured out, okay, if we have an equation that has a square root from where we're starting from, then we need to unsquare, or if it's squared, we need to unsquare it. If it's a square rooted also, then we need to unsquare root it. So whatever it is, we need to undo the state that it's in if that's where it's starting. Okay, it's the simplest way to look at that piece of information. Then we have this is a parallel. I wrote P. That's how I'll label it. Parallel circuit. Okay, now I'm going to get an additional piece of paper for some more notes. Okay, so now we have some, again, not the most information, but we have enough information to fill in everything else, which is the case of what they'll give you unless they have an answer, like what's the answer to this, and then there's not enough information, and one of the answers in the A, B, C, or D will be there's not enough info or something like that. That could be the case. I've seen it before. Okay. So in this case, parallel circuit, we're going to think before we start anything that because we have a parallel circuit, you may just want to draw a visual in your brain if you visualize it. That's good enough for me. It's very sloppy. I'm going to take that out of the camera shot. Okay. This is good enough for me. Okay, now I know that's a parallel circuit, so I'm going to think the fact that the current is actually going to be adding now. The voltage is going to be staying the same. The resistances always are going to be changing. They do not add together anymore, though. They do the weird 1 over, it's called the reciprocal. Take the reciprocal of everything, you get that answer, and you take the reciprocal of that answer. That's your answer to your total. And then your powers always add together to create your power total. So whatever it is, your powers always are going to change between each resistor and equal your total power, whether it's parallel or series. Okay. Now, very simple here. We have our different amount of amps for a parallel circuit. And all we need to remember is that our amps not only change in a parallel circuit, but they also add together. Okay, so we can just simply add these together to get our answer. And another way to do that is what we did before. So I'm going to do 15 plus 30 plus 5. I'm going to add all these together. I'm going to get 50. Okay? And then I'm going to do 60. I guess I'll show you. And then, focus. And then 65 minus 50, which we all know, but it's good to be able to look at it. 15. Okay, so I did 65. I did 15 plus 30 plus 5. Yes, that's exactly what I did. And I did 65 from there minus the 50, which is the answer. Yes, and I got 15. Okay, so nothing should go wrong now downstream. Now, resistances do that weird thing. But there's a problem, and that's the fact that how am I going to get my resistances without anything else? Okay? Well, again, I could get that one constant number and figure where that is in any place in this, is a good way to say it. So I can so what can I do with these given numbers to find out a constant number that'll stay the same? My powers always change. But in a parallel circuit, the voltage stays the same, remember. Okay? So because the voltage stays the same, that's our constant number. So let's figure out the voltage. Try to give you a little pause if you want to think about it maybe. So, handy dandy flashcard, if you don't already have yours. We're going to do... We want E4, okay? I'll take that out of here for now. So, yeah, let's just say that. We want E, but we want E4 is what we want. And because of that, well, I'll write that a little better. I'll write big E4 is what I want. And how I'm going to get that is with R and I, okay? So as we know, ear. E is I times R. Okay. So I times R, and it's not just I times R, it is I4 and R4. These are two numbers that are changing. They're the changing numbers. But because of that, they're going to be able to give me E4. Okay? In this case, which is going to be everything else, but that's what's going on. These two changing numbers are going to give me this resistor's answers. Okay? I4 times R4. I times R is E. Yes. Okay. So now, 15 times 15. We should probably all know that. But 225. 225, 15 times 15, still write it down, equals 225. 225. Okay, so 225 was 15 times 15. Yes. Okay. So now that I know that, now I know everything. Or I know all my, I know everything. I know all my voltages. Okay. And because I know all my voltages, I have now that same number, which then I can use with this changing number to figure out my other changing number. Okay, so that's what it is. You need to figure your other changing numbers. You need that constant number that runs across everything is a good way to do it. With the, especially with the information that we had this, what we had to actually do. Okay, so now we need to figure out R. So now we're looking for, where am I going to write this? Don't get mad at me for writing it up here. No, I won't do that because it's going to make you mad. I can already tell you're mad from that. Okay, so now we're going to go, we want R. Whatever the R is, we want all of them. So to figure out the R, what we're going to be doing is we want E and I. Okay? So we have R, and we want E and I. So it looks like we do E divided by I. Remember, whatever it is, if it's over it, it's divide. If it's next, it's times. So 1R, E over I. I kind of want already that enough, but in real life, I'd always, then of course, always double check and say, okay, R, E, I. There's a chance if you thought too quick, you do I over E or something. Then you double check and you go, oh, whoops, don't want to do that. Okay. So now we have that. Get the flashcard. Get out of the way. Don't got to think about it no more. All I got to think about is whatever I'm doing, I got to do E over I. So I just got to analyze. It's E over I. Oops, little bump. Everything looks good. So it's E over I. I always like to start with that base number. And in this case, we're dividing. So we have to actually start with whatever number we're starting with, that E. So that's good because now I can start with that number that's staying the same. So it's easy. So I just got to do 225 divided by blank. 225 divided by blank. 220. Real easy. So let me actually write that down. I'm going to get 225 divided by I. I didn't say divided by. Divided by I. Okay? And yes. Okay. Now let's do that. 225 divided by I. So now I'm just going to do, I like to start from the total. 225 left to right. 225 divided by 65 equals 3.461. Keep the thousandth. 225 divided by 15 is 15. Okay, so you're already seeing something interesting here. Then, or maybe you're not, but you might. 225 divided by 30, 7.5. 225 divided by 5, 45. And remember, it's a parallel circuit, so we see that this is smaller than all of these. So that looks good. That's what you want. Remember, the resistance is smaller than the total resistance is smaller than any of the resistances on any of your individual resistors. Okay, so it's good to be able to solve for that and to double check, but let's maybe do everything at once and separate categories. So let's maybe keep a category of double checking at the end and do it quickly. And for now, we'll be doing just powers. So we'll just we'll complete everything. Let's do chunk by chunk. And we're still in the entire chunk of finishing this thing. So let's finish this. And we have P. Okay? And P is also a changing number. So because of that, we're going to need to figure out, of course, all of them and not just one of them like we could with our voltage. So we figure out all of the different P, and to figure out P, let's look at the smallest numbers we could be working with that hopefully aren't a bunch of decimals. Okay, well, we could be working with the R, which is smaller numbers, or we could be working with E, which has the same number all throughout, even though it's a bigger number, but we don't have 3.461, which might be based off 3.46 on the answer, or 3.461, and you may not know. It looks like I'll probably want to use 225, even though it's bigger. It's kind of simpler in nature. Okay, so that's what I'm going to pick. Now I'm looking at something where I have P, and I want to use E and I. Okay, so E, I want I, or that's what I want E and I for P. So what do we have? So I have P, and I have E and I. Oh, it looks like I times E equals P. So that one's pretty simple. Okay. So let's write that down. P is I times E, or in other words, pi, because I write them down as how they are already timesed, like ear, pi, Peter. Okay, so pi, P-I-E. We can double check that. We already know that one. P, I times E. Double check, guess that's what we're working with. Okay, so we have 225 times blank is what we're working with, because multiplying, you can do, of course, either way. 6 times 2 is 12. 2 times 6 is 12. You can do that. But if you do 12 divided by 6, you have 2. Then if you do 6 divided by 12, you have 0.5. So different when you multiply or divide. Subtract, multiplying and multiplying, you can flip it either way. And adding. I almost said not with adding for a second. I don't need think about too much random stuff. Let's keep it to this stuff. 225 times blank equals my P. I want to know my P. I got my I times E. Okay? Or I can do E times I. Remember, it doesn't matter. So I'm doing 225 times blank. 225 times 65 equals 14,625. Woo! Okay, oh, shit. And then I'm going to do 225 times 15. 3,375. Then we have 30 times 225. I did backwards, same thing. 6,750. 225, 30, 6,750. And I have 225 times 5. 1,125, or how I'd say to my head, 1125. Then 225 times 15. Now with that I get 3,375. Okay, everything's looking good. And now to double check everything, I could do the double checking. Remember, the powers always add together, so whatever I'm doing I could always just do add all the powers. So start 3,375 plus 6,750 plus 1125 plus 3,375. Should probably tilt this so you can see it better. And I get 14,625, which is what I had for my total. So everything's looking good there. And my voltage, of course, those are the same, so don't really need to double check anything there. We already figured out the basically to figure out our answer for our amps, we already added these and subtracted by that, so we basically already knew that. And we could also already see that 15 plus 15 is 30, 30, 65. You probably may not have as simple of numbers though. So whatever you want to do, I don't think you need to double check that because you already basically got your answer through doing a similar method. But if we want to do our resistances, then we could do that kind of thing that looks more complicated on paper than it is on a calculator. So on a calculator, it's really simple. Just do 1 divided by the first one plus 1 divided by the second one plus 1 divided by blah 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 the next one plus 1 divided by the next one. Okay, and I could double check that I didn't fuck something up. Sorry for my language, it's far enough in the video. So 1 out of 15 plus 1 out of 7.5 plus 1 out of 4.5 plus 1 out of 4.5. Oh my gosh, I did mess something up. Which is funny, I normally, just being honest, don't in real life. So it's good I caught that on the video. So I got 0.288. Okay? So I'm gonna write down to the thousandth, 0.288. Then I'm gonna get 1 over 0.288. I'm gonna get 3.47. So it's basically the same thing, it's slightly off. So now let's see what happens if I do 1 divided by 0.28. Now I get 3.57. Okay, so I don't know exactly what it is, but you'll see that on the test. You'll find an answer that it won't be slightly different. You'll find the one that's the correct answer. So whatever it is, you'll figure out the right answer. Oh, I think it's because it was repeating. So like I was saying, if it's repeating, actually, sometimes you just press the number a bunch of times. It gets you closer to what it actually is. So let's do it one more time. Because it actually is 2 point... You can't even see that. 2.8 repeating. So let's try that one more time. And 1 over 0.28888888888. Just type the repeating number. If it's the same repeating number, type a bunch of times. If it's 2 of them or whatever, just do it a bunch of times. And however many times you do it, probably get you closer to your answer. Okay, and what do we get? 3.461. So that's the other method. So you stay in the thousandth or the hundredth. You don't get the answer still. If it's a repeating number, type it a bunch of times. We got the actual answer. Okay, everything's looking good. And I'm pretty sure it's the last, yeah, it's all that I had for you. Okay, so good luck for you if you're going to be taking a test. Good luck to me. And that's it for the practice electrical theory study. If you like this video, let me know in the comments. Give it a thumbs up. Subscribe to see more. There will be a lot more about loads calculations and service calculations and box calculations and random things more having to do with the administrator's test coming up. So get ready for that. Thank you for watching. Till next time, take care and have a good one.